Okay, in this video we are going to look at how to find the full range Fourier series of a function, half range cosine series of a function, the same function, and then half range sine series of that same function. The function we're given is y equals to x, defined over the interval 0 to 2. So in the first instance, in part A, we're going to make a sketch of the periodic extension of the function. It's just periodic extension. And then we're going to find the Fourier series, which defines this extension here. In part B, we're going to make a sketch of, this time is the even periodic extension of the function, and then the corresponding series is the sine series. And then lastly, the same function, this time we're going to find an odd periodic extension of the function, and then associated with that is the sine series. So let's get going. So in the previous video we mentioned that if the question says just Fourier series for full range Fourier series, then the given interval is always taken to be the full range. So here goes. So this function is defined between 0 and 2. So it's just a straight line, y equals to x. So if that's 2, then that's the given function. So the periodic extension over the other intervals of 2 is going to reproduce exactly the same function. So if you like, if you cut this and paste it in the next interval, it should give you the same thing. So it's going to look something like this. So that's now going to be 4, and then that's going to be 6. Same thing this side, it's going to be negative 2, it's going to be negative 4, etc. So that's what the periodic extension of this function is going to look like. Now, so as we mentioned before, whenever we are finding the full range series, the question is always, is the extension odd or even? Okay, so we know this function is odd, but since it's defined over one side of the origin, then the extension may be odd, may be even, maybe neither. If you look at this, if you try to reflect this line, it's going to go like that. So it's definitely not even. It's not odd, because for odd you reflect it here and then reflect it here, so it's going to go there and then go there. So this extension is neither even nor odd, which means we expect that there's going to be some cosine terms, and there's also going to be some sine terms. Now the other thing we said, since the given interval is 2, whatever the given interval corresponds to 2L, so 2L is equals to 2, and so L is going to be equal to 1. So then we find the Fourier series. We're going to start with the ANs. We are going to use the formula for the full range cosine. So A, start with A0, which is 2 over L, integral it's going to be 0 to 2L this time, f of x dx. So L is 1, 0 to 2, it's just 0 to 2 is this interval here that's given, x dx. It's going to be 2x squared over 2 from 0 to 2. This is going to give us 2. And then for an, going to have 2 into the integral from 0 to 2, x cosine n pi x over L. But L is 1. So it's just going to look like that. We integrate this using tabular integration. So x1 0 cosine n pi x 1 over n pi sine n pi x, the negative 1 over n squared pi squared cosine n pi x. So that term is going to be plus, that one is going to be minus. So we call this thing I. So I is going to be, remember these are 2 there, 2 into, so it's going to be x over n pi sine n pi x plus 1 over n squared pi squared cosine n pi x from 0 to 2. When x is equal to 2, there's going to be 2 there, there's going to be sine 2n pi, which is always 0. Yeah, and then when x is 0, that's going to be 0, so that term is going to be 0. Then we come to this term here. When x is 2, it's going to be cosine 2n pi. So cosine 2n pi over n squared pi squared minus, when n is 0, it's going to be cosine 0 n squared pi squared. But cosine 0 is 1 and cosine 2n pi is also 1. So this thing is going to be 0. By the way, when you do this step, we make sure that n cannot be equal to 0. When n equals to 0, already did the thing there. Okay, then for the bn, so we are going to have 2 to the integral from 0 to 2x sine n pi x this time. If you do the same integration by parts or tabular, then this is what we find. N must be different from 0. So that means we can write the Fourier series of this. It's going to be a naught over 2. A naught is 2. So a naught over 2 is going to be 1 minus, when it comes to the terms inside the summation, it's only going to be the sine terms, because for the cosine terms we got 0 when n is bigger than 1, and for the cosine terms we got that minus 2. So let's do this plus here, minus 2 over n pi sine n pi x, n from 1 to infinity. If we write out the first two terms, or if you like here the 2 and the pi, we can take out of the summation because they don't depend on n. So that's what we're going to have. The first few terms of this 2 over pi are going to be sine pi x over 1, then sine 2 pi x over 2, then sine 3 pi x over 3, etc. So that's the full range expansion. So that completes question A. We're now going to go to question B. So in this case, we're making an even extension of the function. So B part 1. Even extension of the function. So again, we have so this is a function we have. We want an even extension, so it's just going to be a mirror reflection of this thing in the vertical axis. Okay, now remember, so if this is a half range situation, it means 0 to 2 is half of the range of interest. Just one moment, maybe we'll talk about that. Okay, so actually maybe I should do this in a different color, so let me do it in green as before. So it's going to look something like this. That's -2. So that's the full range. So that means the full range has got 4 units. So from here to 6 we must have the same thing, and then same thing this way, and you can see obviously that is an even extension. Now when it comes to the computation for the half range cosine expansion, so 2L is going to be equal to 4, so L is going to be equal to 2. Okay, so when we do the calculation, then automatically Bn is going to be 0. So it's going to be 2 over L, then from 0 to 2, which is L, then x cosine n pi x over L dx. Okay, and then again we do that computation. So maybe let's do this one. So x here, 1 here, and 0 there. That's our tabular integration. Cosine n pi x over 2. So this is going to be 2 over n pi sine n pi x over 2. And the next one is going to be negative. It's going to be 4 over n squared pi squared cosine n pi x over 2. Those two multiply out, and those two got a minus there. So we got this thing I. So this is what we're going to have. So I is going to be 2x over n pi sine n pi x over 2. The other term is going to be plus 4 over n squared pi squared cosine n pi x over 2, 0 to 2. Right, then so when x is 2, that's going to be 2 there. That's going to be sine n pi. Sine n pi is always 0. When x is 0, that's going to be 0. That's going to be sine 0. So that term is not going to give us any contribution. For the second term, when n is 2, so let me just write this outside here. N squared pi squared. When n is 2, this is going to be cosine n pi. When x is 2, when x is 0, it's going to be cosine 0, which is 1. Okay. Now, cosine n pi is negative 1 to the power n. Okay. So this thing is going to add up this when n is odd. So when n is odd, this thing is going to give us minus 8 over n squared pi squared. N is odd. And then when n is even, this thing is going to be 0. Okay. Now when we do this integration here, as soon as we divide by n, then we must exclude n equals to 0. So we still need to find a naught. When n is 0, it's going to be 2 over 2 integral from 0 to 2 of x dx. This gives us 2 as before. So that means the half range cosine expansion is going to be a naught over 2 is 1. Then you have got these terms here. There is 8 over pi squared. Then here we are going to have n squared. So so remember, this is how our terms look. So we're going to have cosine n pi x over 2 all divided by n squared, and then n odd here. Okay, however, we can write that a bit more elegantly as follows. So 1 minus 8 over pi squared. So n odd is going to give us the 2n minus 1. So n equals to 1 to infinity. It's going to be cosine 1/2 2n minus 1 pi x. You can put brackets here. And then in the denominator, we're going to have 2n minus 1 all squared. So that's going to be the cosine half range cosine expansion. 19 minutes. We're going to do the half range sine expansion in the next video.